Humans can engage in a range of really complex behaviours. So for example, you might have spent last weekend baking a cake or playing chess, or maybe organising a holiday. All of these activities involve planning. Planning is defined as the cognitive process which allows us to generate a sequence of states by which we can achieve a goal. So for example, if you're playing chess, you might have to think several moves ahead in order to work out how to capture your opponent's queen. However, planning is computationally demanding, both for biological systems and for artificial agents. Imagine navigating in a graph composed of a series of states such as this one. You start from a particular state, say S, and you wish to reach a goal state, G. One naive solution to this problem is just to consider all of the possible trajectories. But this solution doesn't scale well to large problems. For example, in complex graphs, the number of possible trajectories increases exponentially with the distance to the goal state. One solution to this problem is to cluster states hierarchically. Take, for example, the problem of navigating in a subway network, such as the London Underground. Subway networks tend to be organised hierarchically. States, or stations, are organised into lines or clusters. This reduces the complexity of planning in the network. So for example, if you're at Notting Hill Station in the London Underground network and you want to get to King's Cross Station, you don't have to consider all the intervening steps en route. Rather, you can just consider that you have to take the Central Line and get to Oxford Circus and change to the Victoria Line to arrive to King's Cross. So by clustering the stations into lines, we can reduce the computational burden of planning.
In our study, we wanted to know whether humans represent their plans in a hierarchical fashion. And so what we did was we asked them to first familiarize with a subway network, a virtual subway network, in which they learned the names of the stations and the lines. And we put them under functional magnetic resonance imaging. And we asked them to perform journeys while they couldn't see the map anymore. The only thing they could see was the starting point and the end point, and they had to navigate from one to the other one by using one of 4 possible actions, which were north, south, east, or west.
We had to make some assumptions about how plan complexity would relate to behaviour and to brain activity. So we know from past studies that response times tend to be slower when decisions are more difficult. And so we assumed that there would be a positive correlation between participants' reaction times when deciding where to move and the complexity of the plan. Specifically, plan complexity under a non-hierarchical policy should decline linearly as you approach the goal. Under a hierarchical policy, plan complexity will drop sharply as you move from one cluster to another. So we were able to measure participants' reaction times and ask whether they were better predicted by a flat or a hierarchical measure of plan complexity. We found that they were best predicted by a hierarchical measure of plan complexity.
On top of the behavioral measures, we also use fMRI, or functional magnetic resonance imaging, in order to look at which brain regions could be reflecting also these flat or hierarchical representations or complexity of the journeys. We found these regions, the DMPFC or dorsomedial prefrontal cortex, that was reflecting the complexity of the journey in a hierarchical way. And so we decided to ask further to see whether on top of that it might also be encoding the actual context in which you currently were, which would correspond to this hierarchical representation. So we moved to a multivariate technique called as RSA for representation similarity analysis that allowed us to see how consistent the pattern of activity in that region, in the DMPFC, was for each of the lines or contexts in the subway. And so for example, if you're in the red line, you could see that the pattern was very consistent there. But then suddenly they would switch to a blue line, and then the pattern suddenly would switch. And so in a way we know that the information about the line is encoded in this region as well.
So one interpretation of this finding is that the dorsomedial prefrontal cortex is responsible for encoding hierarchical plans in such a way that it allows humans to plan in a computationally efficient fashion.